Good afternoon, class. This video provides an introduction to the first derivative. And in particular, we're going to look at how you can find the first derivative of polynomial functions. We have one rule here at the top of the page. This notation means the first derivative with respect to x of x to the power of n is equal to n times x to the n minus 1. So the exponent becomes the coefficient, and from the exponent we subtract 1. So let's look at some examples together. In example 1, we have y is equal to x to the power of 6. So in applying the rule, we have the value of n is equal to 6. And that means the derivative can be formed like this. First of all, it's really important that we change the notation on the left side to dy by dx. This means the derivative of y with respect to x. On the right side now, we apply the rule and write 6x to the power of 5. And that's it. So here's a second example, which is similar, except we have a coefficient 5 here already. Dy by dx is formed by taking 5 and multiplying it by the derivative of x to the 8, which of course is 8x to the 7. So we end up with 40 times x to the power of 7 as the derivative of 5x to the power of 8. So this is y, and this is dy by dx. Okay, question 3 is important for a couple of reasons. First of all, one thing to note is that the independent variable is now t instead of x, and the dependent variable is now I instead of y. And that means when we go to find the derivative, it will look like this, di over dt. The other importance, 6 over t cannot be differentiated. We need something of this form before we can begin. So we have to rewrite 6 over t by using a negative exponent. 6 over t to the power of 1. So 1 is implied here as the exponent. That's the same as 6 times t to the negative 1. And therefore the derivative has the 6 out front multiplied by the derivative of t to the negative 1, which is negative 1 t to the negative 2. So we end up with negative 6 times t to the negative 2. And this can be rewritten negative 6 over t squared. So the original function 6 over t has a derivative equal to negative 6 over t squared. Okay, and again, it is important that we change the notation from I to di by dt at the moment this rule is applied. Okay, let's try problem 4. Problem 4 has to be rewritten before we differentiate, because again, we need something of this form. So we have to remember this is the same as negative 2 times x to the 4/5. We use a fractional exponent when we have radical form. So this function is still the same as this one. They are both y. Now we're ready to form the derivative of y. So dy by dx equals. So the negative 2 gets multiplied by 4/5 x to the, from 4/5 we must subtract 1. 4/5 minus 1 is the same as 4/5 minus 5/5, and therefore it's negative 1/5. This will give us, after multiplying here, negative 8/5 x to the negative 1/5. To complete this, we'll make our exponent positive. So negative 8 over 5x to the positive 1/5. So the power goes into the denominator. And finally, now we can use radical form. So we have to remember that the 1 would remain here, implied, and the 5 is the index of the radical. So we end up with negative 8 over 5 times the 5th root of x as our final dy by dx. Okay, so a couple of things to remember. If the original starts like this with a positive exponent in the denominator, the final should look the same with a positive exponent in the denominator. And similarly, if the original starts with radical form, the final version should also include radical form. Okay, let's take a look at question 5. This is functional notation. We say f at x. So when we form the derivative, if we have functional notation, the derivative is called f prime at x, and it looks like this with a little mark here. Okay, don't forget that x is the same as x to the 1. And so the derivative would look like this. The 12 gets multiplied by the derivative of x to the 1, which is 1x to the 0. So what do we have? We have 12 times x to the 0. But x to the 0, of course, is equal to 1. So our answer is 12 times 1, or 12. Soon it will be very automatic for you. The derivative of 12x is 12. The derivative of 1/3 x is 1/3. The derivative of negative 7x is negative 7, and so on. Okay, how can we differentiate number 6? It doesn't appear to have the form that we need. We can make it of that form if we make it 11 multiplied by x to the 0. Of course, this is allowed because x to the 0 is 1. And then when forming the derivative, dy by dx, the 11, of course, gets multiplied by 0 in forming the derivative of x to the 0. The very first thing that happens is the 0, of course, comes forward. I mean, strictly it would be 0 times x to the negative 1. But the key is there's a 0 in there, which means dy by dx is 0. So the derivative of 11 is 0. The derivative of 0.65 would be 0. The derivative of pi is also equal to 0. The derivative of any constant on its own is always 0. Okay. Now what we're going to do are full polynomials, thus the title of today's lesson. So the first thing to do, of course, is to eliminate the radical form. So we're just going to rewrite function y using a fractional exponent here. Now, the fraction will have 3 in the numerator. What will the denominator be? The denominator is always the index. If there's nothing written here, it's assumed to be a square root. So what we have here is x to the 3/2. 3x, if it's helpful to you, you can change it to 3x to the power of 1. And as for 12, if it's helpful to you, you can make it 12 times x to the 0. Now we can form the derivative. So, what happens when forming the derivative? Well, the 1/3 is multiplied by 3x squared. 1/3 is multiplied by 3x squared. So that will just be x squared. Minus, so the sign will follow. Then we do the derivative of x to the 3/2, which is 3/2 x to the 3/2 subtract 1 is 1/2. Plus, now 3 is multiplied by the derivative of x to the 1. So 3 is multiplied by 1x to the 0. And then minus 12. 12, of course, is multiplied by the derivative of x to the 0, which is 0x to the negative 1. Okay, so what do we end up with? This is just x squared minus 3/2 of x to the 1/2. X to the 1/2 is the same as the square root of x. Implied right here is the 1, and implied right here is the 2. Plus 3, because this is 3 times 1, minus 0. So here is our full derivative. It's x squared minus 3/2 times the square root of x plus 3. Okay, so the derivative of 3x is 3. The derivative of the constant negative 12 is 0. Okay, one last example for today. So begin by rewriting the first term will be x to the 2/3 multiplied by 5. For the second term, we use an exponent of negative 3. And now we're ready to form the derivative of each term. Okay, so 5 will be multiplied by 2/3 x to the, we have to take 2/3 and subtract 1 from it. So that's 2/3 minus 3/3, which is negative 1/3. The negative 2 will be multiplied by the derivative of x to the negative 3, which is negative 3x to the negative 4. Plus, okay, if it's helpful to you, remember you can put your 1 here and your x to the 0 here. But perhaps by now you're starting to get the hang of this. The derivative of 5x will just be 5. And pi is a constant. Pi is a number. And so is pi squared. It's just a little bigger than 9. So the derivative of that number is 0. Okay, but if you want, you can make this 5 times 1x to the 0 minus pi squared times 0, if that helps you. Okay? And so what do we have now? We have 10 over 3 x to the negative 1/3. This is now negative 2 multiplied by negative 3, so plus 6x to the negative 4 plus 5. Okay, so we can start to maybe even taper this down a little bit, right? From up here, perhaps you could see what would the derivative of this term be? It would be 10/3 x to the negative 1/3. Because we do 2/3 times 5 is 10/3. And then we subtract 1 from 2/3. What would the derivative here be? Positive 6x to the negative 4. Because the negative 3 comes forward, multiplies by the negative 2 to give us 6. The derivative of 5x is 5, and the derivative of the constant pi squared is 0. Okay, now we have to make these exponents positive. So they need to go into the denominators like that. And finally, the one here with the fractional exponent needs to be written in radical form. In so doing, the 3 is the index, the 1 would be implied here. And now we have our final results. Okay, so we just did 8 problems together, focusing on the derivative of polynomial functions. I put a little reminder here at the bottom of a couple of the exponent rules that we had to employ along the way. Remember, it's really important that you change the notation on the left-hand side in the step where you apply this rule. So in the step where you are changing the exponent by subtracting 1 from it, that is the moment when you change the notation. Okay, so as soon as the exponent changes by subtracting 1 from it, that's when the notation must also change. Okay, thanks for viewing the video. Suggested problems will be posted for you in Blackboard. Have a good day.